Welcome back to the evening session. So we'll have Felix Schulze tell us about a relative entropy for Ricci standards.
Thank you, Matt. Thank you, Jonathan, for the invitation. It's a really pleasure to at least virtually be in Australia. I'd like to be back in person at some point. Yeah. So this is joint work with Alix Deruelle from Paris Jussieu. So now first sort of we'll quite give a long motivational part. Okay, so in space there might be questions there. So let's consider Ricci flow here. So good, yeah, everyone knows this. TDTG is -2 times Ricci of G. Okay, I'm not saying more since all of these are mainly experts here anyway. And the question is what you want to sort of understand, sort of ask here is, can we understand solutions coming out of, let's say, Euclidean metric cones? So a cone is a cone over a compact manifold N with the cone metric G cone is dr² plus r² Hn is the Riemannian metric on N, and we fix the cone point as the base point. And I want to give the first and sort of want to explain why I think it's interesting to actually study these solutions. Now here's the motivation. Otherwise it might be sort of a bit artificial. Why do you want to do this? So the first point is, I think, is you want to look at some definitely interesting question is if you want to look at long-time behavior of non-collapsed solutions. Okay, let's assume we have a non-compact manifold G, family of solutions. And we assume, for example, that the Ricci curvature is bounded from below for all time. Let's assume we have positive asymptotic volume ratio. Yeah? So if R goes to infinity, R to the -n volume of G of t, BRP is greater or equal than some C naught is greater than 0 for all t positive. And you can actually check that this asymptotic volume ratio, if it's positive at some time, it stays constant and positive for all positive times, so that you can easily check this. And okay, so now very natural question is, now you want to look at the long-term behaviors, you can look at the blowdown. So you can look at Mn, lambda I G, lambda I inverse T, T positive, you fix a base point P. Does this subconverge to an expanding soliton solution as lambda I goes to 0? Very natural question. Now the other question is, for example, the natural scaling would be that you want to have the Riemann of G of t goes like C over t, so type 3 solution, then this is invariant under the scaling. But the question is actually, do we really need this? My guess is we don't need it. So if you look at this recent work of Bamler, I would say if you adapt this work, you should actually be able to do a blowdown and without a curvature bound, get at least some kind of weak expander. So I think that would, for example, be interesting, maybe even approachable already under some curvature conditions. Do something like this. Can you prove that in a weak sense you're going to an expanding solution, which is very interesting because that sort of pins down the long-term behavior. Okay, now this is sort of the first thing, but you can also look at this for something sort of at close to time 0. Now, what is sort of the other part is, if you look at Ricci flows from non-collapsed Ricci limit spaces. Okay, now let's recall what is a Ricci limit space. So it's a metric space X, as a topological space X with some metric D. And you assume that this is the limit in Gromov-Hausdorff as I goes to infinity of some smooth Riemannian manifold DGI PI, where we assume that we have a lower Ricci curvature bound, let's say -1 by scaling, and when you have that the volume of GI, let's say of the ball PI1, is greater or equal than delta is positive. So we have non-collapsedness. You can even think about if you want to have this everywhere. And now, for example, so what is the setup? You can, for example, in dimension 3, you can check what Miles Simon did already a long time ago. Huh? He showed that under this assumption, I think you need sort of, there you need uniform non-collapsedness. There's a T positive and a Ricci flow. So you have this limit space here, and which you write as the limit I goes to infinity of mi d gi pi. Now you have here, you can flow these by Ricci flow. So you get here mi gi of t, and they now exist for a uniform time capital T. P, you have curvature decays like C over T. And they then here actually, they then converge to a Ricci flow M G of T. Now T is now only on the open interval, time 0 is not there. And you can actually check, you get good control on the distances. So this converges actually even stronger than Gromov-Hausdorff. Really the distances, the induced distance down here. This induced distance from the metric that converges in a very strong sense to the initial distance. Okay, so what you get sort of a Ricci flow coming out of the Ricci limit space. And why is this interesting? Because, a Ricci limit space, if you just have a lower Ricci curvature bound, you have no PDE to work with. You have only sort of a sub-solution to a PDE. But if you have a Ricci flow coming out of it, you have a parabolic solution. So you can use parabolic techniques. Otherwise, you have not only an inequality, but you have a solution. So that can turn out to be very helpful. So where was this, for example, used? Simon Topping used this idea, and they constructed a local solution to Ricci flow to do this. They proved the Anderson-Kolding Chigotian conjecture with this, which said in this case that X3 is Bi-Herder to some manifold M3, and more or less the Ricci flow here actually constructed the manifold, which is an interesting thing. The Ricci flow constructs the manifold, which otherwise you don't get. So it's very interesting, and this is dimension 3 from dimension 4, and it's open. So you can try, then you expect a singular set. Now you can kind of ask, okay, can you do the same thing in higher dimensions? With some assumptions maybe. Now, what can you do now here, or even in 3 dimensions? If you want to understand sort of the regularity a bit more, if you take a point Q and M, and you assume you have this Ricci limit space here, okay. You can identify X with M. You can talk about points in there in that sense. And let's take a tangent cone. So we want to look at the regularity. So we take tangent cones of the Ricci limit space at Q, i.e. sort of we have that M lambda to the 1/2 D. You fix Q. This goes as lambda I goes to infinity. You take a subsequence. And this gets to some Euclidean cone over some metric space. And now, but you can do the same thing here. Then these flows here we have M lambda I G lambda I to the -1T Q. They converge to a flow M prime GT, and that exists for all positive times. Some Q bar here, and that again here you can show converges in a strong distance sense to this cone. So you get a solution here coming out of this tangent cone. And now you can try to understand, sure, if you understand sort of the regularity of the tangent cone, you get a lot of information. Can you use this Ricci flow to say something about this tangent cone? So the question is, use M prime G of T, T positive, Q bar, to understand the regularity of MD. I want to understand the tangent cone, so then we get an equation on there. It's at least parabolic. We can try to use this Maybe also in some geometric applications, maybe the flow we get actually carries still more information than the limit space. And so we can try to sort of transport the information out of the flow, then still back to the limit space. So that would be the second application. Here's another one. Now, I guess everyone has seen by now sort of these weak Ricci flows by Bamler. So we have a family of metric spaces, some more data, which I don't know at the moment, yeah. And assume we would be so far and could produce a Ricci flow through singularities, yeah. I guess in 3 dimensions, this is established by the work of Lott and Kleiner and Bamler and Kleiner. Okay, let's assume this. Now let's assume that xt dt, shifted time, has an asymptotically conical tangent flow at P0. We have a singularity, we have a type 1 tangent flow. We don't need a type 1, it can be weak one. We know by Bamler they're also weak ones, and assume that the shrinker is smoothly asymptotically conical. Now assume, so this is the assumption now, assume we would know uniqueness of the AC tangent flow. So what would this imply? And you can check it works for example, for mean curvature flow. You can see this very easily, that actually this, so you have a singularity at time 0. Yeah, it's not time 0, you have a shifted time that actually x0, d0 has a conical singularity at P0, and this is actually modeled on the asymptotic comb of the AC shrinker. That's what you get. You get that at time 0, this thing, you have the singularity. Now, so what you look then here, now if you look at your flow, look at xt lambda I to the power 1/2 t lambda I inverse t. P, you take the base here, lambda I going to infinity. This then goes for t positive. So you have to, sorry, I should take here t positive. This goes to a Weakritchie flow coming out of the cone. So you see, this is another example where actually flows coming out of cones naturally appear. Yeah. So what is the question is here again? So what is about what what can you say about regularity? What is the, and so this should be sort of one mechanism which might introduce non-uniqueness into Weakritchie flows. Yeah. There's no one for mean curvature. I'll say about something like this later. And now I'll talk about mean curvature flow. But that should be the same thing should be happening here. There is, for example, work by Angenant and Knopf, which show that there, in the rotation symmetric case, there are non-unique evolutions of cones in the Ricci flow as well, in higher dimension, I think from dimension 5 on. Okay, now let's go, since you all know mean curvature flow well, let's go to mean curvature flow, and then maybe sort of some more ideas become clear. So if you look at mean curvature flow for hypersurfaces in Rn+1, so take Euclidean background. Okay, now let's take a cone over some n-dimensional submanifold of the sphere. Yeah, okay, you can take the smooth if you want to. And then Illmann has shown, and this is rather easy, we can always construct an expander, gamma, which is asymptotic to CF, to this cone. And what you can prove is that's actually how you get it. It's a local minimizer of this expander functional e to the plus x squared over 4 d mu. And you see, this is not such a great functional because on a cone, this is always infinite, anything non-compact, but you can still sort of talk about local minimizers. Say under local perturbations, it should be a minimizer. That's actually how you construct this. You take Dirichlet problems and let the boundary go out to infinity along the cone, and then you show that this actually converges to a local minimizer. Now you can always construct. So this is the nice thing for mean curvature flow. Now, there's one other thing for mean curvature flow that you can do. You can look at the level set flow of the cone. And now think of the case that actually the level set flow flattens. Yeah? So C of t, t positive, you want to have C0, C. So these are closed sets in Euclidean space. And think of this actually having positive n+1 dimensional measure. Yeah, so it's flattening. Yeah, but what you still get is, the level set flow is unique here, even in this non-compact setting. So from that you get it self-similar. So Ct is just square root of t of C1. Even if it flattens, the evolution of the cone is self-similar. Okay, and then you can ask, okay, you can look, for example, you can ask, okay, do the boundaries of this level set flow, are these still nice mean curvature flows? Yeah, and you can, for example, this was there was in the two-dimensional case, there was sketched by Ilmanen, and in this recent paper with Toy, Chodos, and Mantulidis, one of the byproducts of the stuff we did there is that you can always prove that the boundary of C1 is a union of, let's say, smooth, let's say it has codimension 6 singular set, outward minimizing expanders. So this level set is always on the outside. It's actually a nice boundary looking like expanders. Now I'll give you an example. Many of you will have seen this. Yeah. So you find this in Ilmanen's notes. Take a shallow double-lobed cone. Yeah, the rotation is symmetric one. So think of like this here. This in R3. Yeah. So you rotate this around. Yeah. This is with a small angle here. Yeah. Okay. Now, then you have two different evolutions of this cone. Yeah. So there's a double sheeted evolution. Yeah. This upper cone here is a graph over this plane here. Yeah. And the lower cone is a graph over the plane. There should be graphical expanders. Yeah. So you have two graphical expanders, which is sort of coming out like this here. Yeah. Okay. And now there's another expander here. At least I guess you can by now can find it numerically. Yeah. And that looks like this. It looks more or less, it goes in, it's then here very closely asymptotic to this other expander, and looks like this. So you see, that would be, for example, the boundary in this case of C1. Yeah? So C1 here would be this whole bit here in here. Yeah? And that would be the boundaries. Yeah? So you get two expanders. So what should you compare this with? This is like if you want to construct with the soap film, want to construct a piece of the catenoid. Yeah. So these are the two disk type solutions, and that's the catenoid. Huh? Then you should expect there should be actually an unstable catenoid in between. Yeah. So there should be another one. So there should also be an unstable expander in between. Yeah. And so one interesting thing you notice here when you look at the asymptotics here, that both of these converge to the cone, but they actually converge much faster to each other. Yeah. So these here are sort of convex, or like concave down here. So this expander actually converges much faster here to this single sheeted expander. Yeah. So they go very much closer to each other than to the cone. This will be needed later. Yeah. Okay. And now what you can think about, and I think I heard a talk by Sigurd at some point claiming this was joint work with Dan, but it's never appeared so far. There should be, for example, non-self-similar solutions coming out of the cone in this case. So how do you think about doing this? So, okay, so you think there should be, for example, an unstable catenoid here in between. Okay. Now, what you do, you go to the forward rescaled flow. So then you want to construct an eternal solution where you push off the unstable catenoid, and then that flows to the stable catenoid. And that will give you, for the normal flow, if you undo the rescaling, that gives you a solution which comes out of the cone, which has very initially asymptotics like the unstable expanders, and for very large times converge to a stable expander. There should exist non-self-similar solutions coming out of C. Yeah. And we have to ask Sigurd if they will. Anjan, I think, is this joint with Knopf. I only heard a talk about this several years ago, that in the rotation symmetry case, they said they could sort of really prove this. Maybe one last thing here, or two last things. You can now try to understand this here. And you remember we had this expander function, but which is this expander function is a bit, it's always infinity. And you can now do something. You can define a relative entropy. You say, okay, it's infinity, but maybe if you subtract the right two infinities, we will get a finite quantity where we can work with. So assume we have two expanders, gamma 1 and gamma 2, expanders asymptotic to C, yeah? Then you can look at the following quantity. This relative entropy, and I guess you might have heard Lou already talking about this. And if you go R to infinity, you look at gamma 1 intersected BR of 0, e to the x squared over 4 minus gamma 2 intersected BR over 0, yeah? E to the x squared over 4. Then this exists. Yeah, you can prove it's a nice and well-defined quantity. But actually, so the idea is you prove that these two expanders, you have to beat this exponential weight here. And you have to prove that these expanders more or less decay like e to the r squared over 4 plus the right factor in front towards each other. But interestingly enough, that's still not enough to make sure that it's well-defined. You have to use that one of these is actually a critical point of the functional. You have to use that any perturbation of this is only up to second order. And that only allows you then to do the right computation. If you wouldn't do this with the critical point, even this right decay wouldn't work. Yeah. And what you can, for example, do this here, you can use this, you can prove that you can prove generic uniqueness. That sort of goes back to an idea of Brian White. We did this for minimal surfaces of expanders with vanishing relative entropy. So if you have two expanders asymptotic with the same cone and the relative entropy is 0, then generically for a generic cone, they have to be the same. What you, for example, get for this, you get generic uniqueness of the minimizer of local minimizers. If you have two expanders asymptotic to the same cone, they're local minimizers, you can always then prove that the relative entropy is 0 between them. And now then you sort of know, that's, for example, how you can prove for minimal surfaces that generic boundary data, there's a unique minimizer. And this works. This is a similar thing here. And now let's go to this work of Jacob and Liu, Bernstein and Wang. And this is 19. And this goes back to some work of Alix, who did this for harmonic map heat flow first. So you can extend this actually to a forward monotonicity formula for solutions coming out of a cone. We have just discussed before, there should be solutions which are not self-similar. What is the important first step? And this will be important for what we do later. To do this for mean curvature flow, the solution has to be, just by the avoidance principle, be inside the level set flow. Yeah. Because it comes out of the cone, it might not be self-similar, but it has to be inside the level set flow. But the boundaries of the level set flow are two expanders. And for these ones, since they satisfy a good equation, they're barriers, yeah. And you get sort of in the C0 sense, you get optimal decay estimates at infinity towards one of the expanders. Yeah, since it's codimension 1, yeah. And so this is what you use there. This follows then rather directly from the same computations that gives existence of this relative entropy. So what you get then is that the blowups and blowdowns of such a solution converge to expanders. So you have any solution coming out of a cone, you do a blowdown, you see an expander, you do a blow up, you see an expander at the origin. Yeah? For example, Jacob and Lou use this to construct sort of in the low entropy setting, they use this to construct isotopies through asymptotic conical singularities. That's sort of their idea, huh? That this is one of the important things that they sort of don't. They say, okay, anything coming out in the future is kind of isotopic because they can construct these solutions which interpolate between them. Here's, for example, a question which I think might be interesting to prove. Are such solutions always heteroclinics of the forward rescaled flow? So more or less this is asking, is the blowdown and the blow up unique? So can you prove that, take any such solution, do you only get heteroclinics? Does it always flow from an expander to an expander? Or are there other solutions which don't come from an which somehow have blow ups and blowdowns, which are expanders, but somehow they're not unique? So that should be interesting and should say something about. And as you know, for mean curvature flow, this is sort of one of the ideas that non-uniqueness should be introduced into codimension 1 mean curvature flow. Okay, now let's go. Okay, so this is a bit to the end of the introductory part. Are there any questions? Okay, now I'll start with so let's talk about expanding Ricci solitons. So, okay, what are these? These are immortal solutions. G of t, you all know this, t positive, such that G of t only moves by scaling and diffeomorphism. So t phi t star g, where g is a fixed metric. The phi satisfies the following ODE. Gradient f0, composed with phi. Zero, so f is some function, and we want to have that phi t equal to 1 is the identity, and f is some function from m to r. So more or less the diffeomorphisms are created by a gradient vector field. So this is equivalent to saying you have a triple m and g grad f with respect to g, and you have this elliptic equation Ricci g minus Hessian with respect to g of f is minus g over 2. That's an expander. Similar to, okay, let's do quickly some examples. There might be more by now, at least here's the ones which came to my mind. You can actually write the Gaussian, you have a Gaussian expanding soliton on Euclidean space. So this is just Rn, the Euclidean metric, and the vector field is 1/2 r dr. And you can actually check phi t of x is then just x divided by square root of t positive. So that's the diffeomorphism. Then there's work by Bryant, it's unpublished. I think from the thousands. There's a one parameter family of expanding grading solitons on Rn with this metric GC, nabla GF. C is the parameter in 0, 1. And what you have about these, they are rotationally symmetric. So SON minus 1 invariant, have positive curvature operator. So as positive as it gets, and they're asymptotic to these sort of rotationally symmetric cones. So this is a cone over Sn minus 1, dr squared plus cr squared, the round metric on Sn minus 1, and 1/2 r dr is the vector field. Okay, and you see this is exactly sort of you take the flat cone, and then you sort of start sort of decreasing the volume of the sphere, and you get these rotation symmetric cones, And so the interesting thing is Alix was able to extend this sort of use a continuity method to prove that if you take any metric on the sphere with, now you want to have curvature operator greater or equal than 1. So this means the cone has non-negative curvature operator over this. Then you can prove that there exists a unique asymptotically conical expander, asymptotic to this cone with positive curvature operator. Yeah, it's a continuity method, so you get this. Yeah, so in the positively curved case, you get existence, but there's also there's work by just by now a bit quite long ago, Feldman, Illmann, and Knopf. It's also very important to have these examples from 03. This is a, so as far as I know, a 2-parameter family of UN invariant Kähler expanding gradient solitons on this line bundle L minus K over C P n minus 1, where K is bigger than N. And these are asymptotic to the following cone. You take the cone over S to N minus 1 mod ZK. Yeah? You see, it's quite complicated topology already. And and the vector field is I dd bar. I think you take the norm to the power 2p divided by p, and you have p positive. Okay, so now, so these are the examples. Maybe there are more. Does anyone know more examples of expanding gradient solitons? Asymptotically conical ones? Okay, so here are the questions sort of, at least sort of, we would like to address now, or sort of what would be sort of interesting question to ask. Yeah. So given a cone, how many self-similar solutions come out of it? See, because from the discussion before, that's definitely something we should ask. Yeah? What about existence? Well, this is kind of a Dirichlet problem at infinity. Would be very important to do this to get more general existence results for expanders for Ricci flow. And then you can ask, well, when do you get uniqueness? So under which geometric condition do two expanders asymptotic to the same cone have to agree? Could ask that. When can you say? As you know, for Ricci shrinkers, in the shrinker case, it's much more rigid. We work with this work of Kochwan Wang from 2013. We know that if you have two expanders asymptotic to the same cone, even just have to be expanding ends, then they have to be isometric. So this is much more rigid. Okay. Here's, for example, about something from Anjanent and Knopf. I think it's from 19, that there exists a Ricci flat cone, n greater or equal than 5, admitting non-isometric, complete, smooth, expanding gradient solitons. Asymptotic to it. So in some sense, it's interesting if you compare with mean curvature flow. So these Ricci flat cones should correspond to kind of stationary cones, but not minimizing cones. Because if you have an area minimizing cone, you should not have an expander coming out of it. It should be just the cone sitting there. So these Ricci flat cones should be somehow only. So somehow there's something sitting in the singularity of the cone, which allows for these cones to start moving. So even in this case, we have non-unique expanders coming out of it. Okay, now here's the theorem, the first one, and I'll explain a bit the ideas. So last here. Okay, so if you take two expanding gradient Ricci solitons, can even two different manifolds. We just need to talk about ends. Yeah. If we have them both asymptotic, smoothly asymptotic to the same cone, yeah. Cone over S. GC is dr squared plus r squared GS, and you have the vector field with an R over 2 dr over a smooth link. The link would be SGS, a compact link, yeah, compact. Now assume we show we can always do this. We can gauge these two metrics in the right way. G1 and G2 are suitably gauged. Turns out this is one of the important problems to understand the gauge. Yeah. Whereas for mean curvature flow, this is easy. Yeah, just their graphicality is kind of a canonical and good gauge. Whereas for Ricci flow, as we all know, or for Einstein metrics, the gauge is a very important thing and changes the problem quite a bit. Yeah, gauge such that their soliton vector fields agree outside a compact set. Okay, what you do, you just take the flow along the gradient vector field and sort of start identifying these level sets. Take the level sets of the, and then that's the sort of thing you can do. Then you have a good coordinate system at infinity. And then the statement is, there is something geometric, then it's called the trace at infinity. And you look at the following, you take the limit as r goes to infinity of, now you want to kind of look at the difference of these two metrics, okay, but we know that this goes definitely to 0, so we have to scale it up, and you have to actually take e to the r squared over 4, so you blow up very hard and blow up even harder. Yeah? This exists, and this is something which you can call the trace between G1 and G2. This exists in L2 log of C of S of the cone. Yeah. Moreover, you can prove that these two metrics agree if and only if this trace at infinity vanishes. So this is kind of the threshold, exact threshold decay rate. You can pin this down. This quantity always exists for two expanders. If it's 0, they have to be the same. If it's non-zero, they are not the same. This was done before by Alix for the Ricci flat cones. It's a different technique, and you can, for example, check. So this is done by Jacob Bernstein for expanders for mean curvature flow. And we have used a lot of his ideas. See, the problem is here in this case, again, instead of we don't have a good equation first. The equation is only degenerate elliptic. So what do we do here? We have a first a priori estimate. You can get this, that Gi minus G of the cone, you can write this as the Ricci curvature of the cone. That's first order, this is more or less just Taylor, thinking of flowing to time 1 plus O to the R minus 4, for both I. So then you get sort of this natural decay rate is that G1 minus G2 is O to the R minus 4. The Ricci term cancels. That you can subtract. Okay, now let's assume we have gauged in such a way that the two gradient vector fields agree. at infinity, yeah, and we'd say h is the difference in this g2 minus g1, yeah. And then if you linearize the expander equation, you get, as you expect, you get a drift equation, as more or less a Laplace equation with a drift term, Laplace g1 of h plus gradient g1 of f1. This is the right drift here. Yeah? Is this? Now you get something which is quadratic in h, yeah, and you get another term here in this case, which is a Lie derivative in direction of the Bianchi tensor of g1. Huh? This comes more or less from trying to choose the right gauge. Yeah? It's called this plus, where b of h is the Bianchi tensor, is divergence g1h minus 1/2 gradient g1 trace g1h. That's the Bianchi tensor. And you see, this is, this is only a degenerate elliptic system. See, because exactly this term here has second derivatives of h. Yeah. So it's only a degenerate elliptic system. Yeah? So this is something we would like to gauge away here. But it doesn't really work. You can't just gauge it away. But there's one interesting thing. It goes back to work of Brett, yeah? In, I think, 17, who shows that along Ricci flow, this Bianchi tensor, what is h of t in our case here, what we take as h of t along the flow is t times phi t star of g2 minus g1. Yeah? That's in our case. This satisfies a good evolution equation. So in our case, what does this turn? This then turns this evolution equation in time turns into a ODE in the radial variable, more or less. Yeah? So we get, in our case, this is an ODE. Yeah? So the ODE you get for the Bianchi gauge, there is that nabla G1 of F1 of B of H minus 1/2. B of H is some error term which is quadratic in H. Huh? So this is based on the Bianchi identity. Huh? No. Based on Bianchi identity, which says that B of the Ricci curvature of GI is always 0. Okay, so you see this is an ODE. Huh? This is like a DDR. Huh? You get an ODE. So the idea is that these two equations, so this here, more or less this equation together with this equation, this gives you an ODE PDE system. Gives an ODE PDE system. And the idea is that this here, you use this to control the gauge. So the idea is we can't just gauge B of H to 0. That doesn't work. That's what we would like to do. But you can try to do an ODE PDE system, try to control the gauge. Huh? And then what you have to do is, so this follows this work of Jacob. Yeah. So for mean curvature flow, this doesn't appear. For mean curvature flow, you just do graphical and all works fine. Yeah. So the idea here is that you can actually still make this work. Huh? You can cook up a frequency function. Associated to H. So how does this frequency function? This is sort of the standard frequency function. Remember, what is the frequency function? So up to scaling factor, it's usually the Dirichlet energy divided by the L2 norm along the boundary. Huh? Okay, Dirichlet energy here, you have to think we're going to the outside. Huh? Our balls are balls around infinity. So it's an integral over little r bigger than capital R. Yeah? Now, gradient H, I'll say what is H hat squared. You have to play around quite a bit and think what is the right quantity. e to the minus r squared over 4 d mu g. So this is like the Dirichlet energy, that part. And now you have here the L2 norm on the boundary. Where r is 2 square root of f, yeah? Exactly, that should be r, yeah? And h hat is, now you have to take the right rescaling, r to the n e to the r squared over 4 times h. Yeah? So that's what we, more or less what goes to the trace. Yeah? And so this is based on ideas of Almgren in the 70s and Garofalo-Lewin in the 90s. Now, that's what you cook up, and you see the sort of, I think one of the most interesting things is to say, as far as I know, no one has done this before, that you do this at the same time where you have like an ODE at the same time where you control the gauge while you construct the frequency or control the frequency. So you do this, you have to do both things at the same time. You get the right estimates for the frequency, then bootstrap and prove the right estimates that you can still control your gauge at the same time, and then make the frequency to work. So ideally, what we would like, and I think this should also be possible, so n of r, you should get that this is O of r to the minus 2, and n is decreasing in r. So this is what you would ideally get. We don't really get this, but we get enough that we can get the application. I think Jacob gets this for Ricci flow, for mean curvature flow. Epsilon in 0, 1, yeah. So we have to sort of give a little bit up on the decay, yeah. So it should be true. So the constant is not uniform in epsilon. This is why I write O of epsilon, r to the minus 2 plus epsilon, and n almost decreasing. So there's the errors, yeah. And so what are the basic ideas? Yeah? If what you get in the end is, if you look at B of R, yeah, this is exactly sort of this integral along the boundary, yeah, of h hat squared, then you can get these sort of like d by dr here of r to the 1 minus n. B of r is O of epsilon r to the minus 3 plus epsilon times r to the 1 minus n. See, this is like an ODE, which is good. And you get that these Dirichlet energies on the outside. They actually have an identity just by integrating by parts. N of r, B of r, r to the minus 2n minus 1, e to the minus r squared over 4. This is your use. These are sort of the main ingredients, what you get there in the end. And if you do this, and again, you have to again use that one of that, you do this to do perturbations of critical points. So you have to use that, that these are kind of critical points to the right functional. So it's only second order perturbations. So you have to, again, find terms which sort of where you get some cancellations or divergences. So this is that if you have a setup as above, and I'm finished now in a second, as before, then the following limit exists. And let's formulate this in time, in the time-dependent way, exists and is constant in time. So there is a relative entropy also for expanding solutions. You take limit r goes to infinity, and you see this is actually very natural. And what comes up here, you take here f2 of t, set is less than r, e to the f2 of t divided by 4 pi t to the n over 2. This is the time-dependent version. Now you subtract the same thing with f1. Okay, where these vector fields Fi of t are just sort of the usual time-dependent versions for expanding solutions. Phi it star of Fi. Okay, so yeah, see, this is the same thing as for Ricci flow, more or less. Yeah? But the problem is here we don't have for Ricci flow from mean curvature flow, you can just more or less cook up the right barriers and get with the barriers already the optimal decay, at least in codimension 1. And here you have to do this frequency function directly, and then use the frequency function to actually get the optimal decay. And the idea is that you have to control the gauge at the same time. So this, I guess, is in some sense related to this recent work of Colding and Minicosi, yeah, where they prove that for this uniqueness of cylindrical tangent flows of cylinders in Ricci flow, of shrinking cylinders, you get this, you control the gauge in time. From what I've looked, these seem to be in some sense similar ideas. Yeah, so you have to sort of use some of these equations. They should somehow be related to each other. Maybe they found a bit more simple version, but this should be a similar thing to sort of add this for the evolution to control the gauge, to kind of find the right gauge to control the gauge under Ricci flow. Okay, thank you very much, and yeah, happy to hear if there are any questions.
Thanks, Felix. Matt, did you have a question?
I did. It was related to, so one application you didn't mention, I guess, was the existence, this work of UI. She gets the existence of steady solitons as if I'm getting the picture right, I think she takes a limit of expanding.
Oh yes, I forgot this. Yeah. This is the work of Eli. So this procedure that you can use blow-ups of expanders to get translators.
Yeah, so I was just wondering whether there's sort of potentially more to be done there, sort of a greater class of examples.
Then you would need to get sort of better existence result for expanders. And I guess as soon as you get more expanders, you can then also use this technique to construct translators.
Okay. I'm sort of, I hope I'm getting the picture right here. So with the, at least in the mean curvature case, you have these heteroclinics going between the two different expanders.
Yeah.
So wondering if potentially you could, if these two expanders were embedded in families that had limits which were steady solitons or translators in the mean curvature case, whether this might give you existence of
there should be kind of heteroclinics between translators.
Exactly. Yeah. Constructing these. Exactly. So non-trivial eternal solutions, basically.
Yeah. That would be very nice. I agree. That would be very nice. That would be very nice to see. Yeah, one could try, for example, the rotation symmetric case, if just try to see if there's sort of an idea how to, what should this converge to, and which family, which solution should that converge to? And can we see something like this? Yeah, that's definitely a very nice idea.
Cool, thanks.
I guess you already commented on it at the end, Felix, but I was thinking even earlier when you were talking about uniqueness of expanders. Sorry, the forward rescaled flow. So I just sort of had a general question about the techniques between the shrinker and the expander case.
Okay.
So I obviously, like, you have this work with Otis on uniqueness in the asymptotically conical shrinker case. And so, I mean, do you think the techniques are sort of a matter of, making everything work with, now the weight is flipped, or is it a situation where things really break and you need sort of completely new ideas?
What breaks with what?
I mean, what? Like one.
You mean for uniqueness? You need for in the expander case?
Yeah, so either for the uniqueness, but then I also had in mind the Bill and Toby's recent work with the gauge fixing. But I guess you said it's sort of potentially similar there.
I don't get your question completely. So tell me again, sort of.
So I guess, like, so for Bill and Toby's stuff, presumably it's adapted to the shrinker case, or if anything, it would be adapted to the shrinker case, because that seems to be what they care about. And so, I mean,
I think there should be something for the expander case as well. I think there should be something for the expander case as well. And I think actually sort of this, if you want to sort of ask the question about uniqueness of tangent flows for a Ricci flow, in the compact case, it's kind of trivial because you can always minimize this paramount entropy. So then use this idea of Sun and Wang. They did this first, that they showed actually that compact tangent flows in Ricci flow are unique. And but the problem is, as soon as you're non-compact, you can't even construct the right flow. So then I guess one of the biggest problems in all these uniqueness questions in Ricci flow is actually to control the gauge while you try to do this. Golden Minikossi haven't published that yet. They claim they can do it, but I guess it would be very interesting to see if, in what sense sort of you have, then you control the gauge for Ricci flow at the same time. You need the right monotonicity flow. You need a monotonicity formula you can work with, and control the gauge at the same time, and then you can start trying to talk about uniqueness of tangent flows.
I was sort of saying is the approach for shrinkers and expanders in those two situations, do you expect that to be sort of a divergent construction, or sort of two sides of the same coin?
In some sense, it's the two sides of the same coin. The hard part is for the expander if you work with this relative entropy. So the estimates will be much harder. So you have to, always beat the weight. But it should be possible. It should be possible. But maybe a good question is, take this forward monotonicity formula of Jacob and Liu, and try to prove a Voyasevich for that, if you have solutions coming out of the same cone. So you have to then always work against the weight. So you won't be, I think you won't be changing the cone at infinity. So there might be something different. But I would guess, it might be tedious, but I think it would be worth thinking about this if there is a way to get a Voyasevich working for that. And then if you have Voyasevich, then you would see heteroclinics, which I think would be a nice theorem to prove that. Now that is, I think, something one could try and do.
Yeah, thanks, Felix. All right, well, let's I guess Zoom clap again.
Thanks, Felix.